Welcome back everyone to part 3 of Aggregate Planning. In this video, I'm going to cover a complete example of actually applying Aggregate Planning to a situation. Let's jump right into it. Jumping back to our original example, we had product A. We already had the forecasted demand from January to June. And we really wanted to know what should the production plan look like to minimize cost or maximize profits. Should it be a level production plan that is produce the same unit every single month, or should it be a chase strategy where we're really cranking up the production and bringing it down as necessary? What should it look like if we want to minimize costs? Aside from the forecasted demand, we also need lots of other information. Here we're given the list of information that we need to actually formulate our aggregate plan. We need to know some of the cost parameters, material cost per unit, how much it costs in inventory to hold a unit inventory for a given period, how much does it cost if we're to stock out or there's a short stock out event, we have a shortage, how much does it cost to hire a worker if we had to lay someone off, how much do we pay per hour for a worker, what are the costs for overtime. We also need to know the initial number of workers, the initial inventory level. We also know how many hours required to produce a single unit. Because we have finite number of worker hours. There's some constraints on the maximum number of overtime hours for a given employee, and the assumption here is that each worker works 8 hours a day, 20 days a month. And another assumption is that unmet demand is backlogged. So what this means, if there's a shortage in one period, then the next period, the shortage is backlogged. So in the next period, it has to be fulfilled. So these are some of the assumptions and the parameters that we need to actually proceed with our aggregate plan. As with all LP problems, the first and probably the most important step is setting your decision variables. So the decision variables, as the name suggests, are the variables that you can decide, or the ones that you can control. So if you think about it, some of the variables that you think you can control are not actually controllable, or really they're beyond the scope of your problem. For example, on the previous slide, we had the labor rates, the regular wage rate and the overtime wage rate. The assumption here is that that's the beyond the scope of this problem. We can't really change those. We could change the total number of hours worked during regular hours, but we can't really change that rate. We also can't change a policy like a worker cannot work more than 10 hours of overtime in a given period. So those things you're assuming that you can't change. Okay, so in this problem, what are the decision variables? So this is the list of decision variables in this problem. So I can control the number of units produced using regular hours. I can also control the inventory to hold at the end of a period. I could also decide how much units to stock out, or the shortage. I can decide how many workers to have in a given period. I could also decide the number of overtime hours. I can also decide the number of people hired and number of workers fired in a given period. So I may use the word fired or layoff. In this case, I'm assuming those two are the same. The next step is to create the objective function. This is our objective. So what are we trying to minimize or maximize? In this case, I'm trying to minimize the cost, the final cost. So then if you want to create the objective function, we have to decide out of the decision variables that we specified in the last slide, which ones actually contribute to the final cost. In this problem, it's actually all the ones that we specified in the last slide. All of these parameters, all of these variables have a cost component to them that are going to contribute to that final cost, or the objective value. Okay, so all of these are going to be part of the objective function. Now let's actually create the objective function. So we're going to minimize the cost. So we know the objectives to minimize, and the cost components are going to be the regular production. So this is the raw material cost for regular production, the inventory cost, shortage costs, regular wages, overtime wages, hiring and firing. and I've omitted here, but this is really the summation across all 6 months. Okay, so we're summing up for the entire period from January to June. Now, if I were to plug some of these in, I know that the regular production is going to be $20 per unit times my decision variables PT for any given period. My inventory costs are $5 per unit times IT, so you do that for every period. Shortage is $12 per unit for every unit short, ST. And the regular wages, each worker works 8 hours a day, 20 days a week, and their cost is $15 per hour, so 8 times 20 times 15, times the total number of workers for a given period. That should give me the regular wages for a given period T. The overtime wage, the rate is $25 per hour, times OT should give us the total overtime wages. And then hiring and firing, there's each one has a rate of 600 and 800. So now I have all of the expressions necessary. I plug it back in to my objective function, and then I have my full objective function. Now I've omitted another part here. I should really have a bracket here. And really, T goes from 1 to big T. In this case, big T is 6 because we're going from January to June. So this is my objective function. And when we formulate this and we put this, let's say, into an Excel solver, you're telling Excel, I want you to minimize this function by changing these variables, PT, IT, ST, WT, OT, HT, and FT. Change these variables so that it minimizes this function while satisfying all of the constraints. So let's actually move on to the constraints. What are the constraints? So some of the constraints, and a lot of times a lot of students have trouble making LPs because they don't really quite understand the constraints. Some questions to ask yourself to get yourself started is, number of units produced during regular hours. Is that constraint, or can we make infinitely many? So obviously we can, so there must be some kind of constraint. Number of overtime hours. Can workers work as many overtime hours as possible? Again, there's an explicit statement in the problem saying that this isn't true. There's a limit on number of overtime hours for a given worker in a given period. Inventory shortage. Are there any constraints to those? And if you look at inventory shortage, these are a binary condition, correct? Because if you have an inventory, then you can't have a shortage, right? And vice versa. Okay, so these are some of the things you can think about to get yourself started. So let's jump in to the production constraints. We know that production is affected by different variables. The first variable is the number of workers. There's only so many worker hours available, so we have more workers, we're going to have more hours available for production. So we know the variable WT is going to affect our production. Number of regular working hours. Okay, so we know that each worker works 8 hours a day for 20 days per period. Okay, so 8 times 20 times WT gives you the total number of regular working hours available for production in this situation. This is the total number of hours available. We can't exceed this. We also do have overtime hours though, okay, which is OT. And we also know that the required number of hours per unit is 3 hours per unit. So every unit of product A that we produce, it's going to take up 3 worker hours. Okay, so we're actually ready to create our production constraint. A lot of times it's easy to do this by just looking at the units. So I know PT represents my production units, total production units. Okay, and every production unit requires 3 hours of my worker time. Okay, so if you check the units on this, so this is hours per unit, and then PT is unit per period. Okay, so units cancel, you're left with hours per period, or just hours. Okay, we know that can't exceed 8 times 20 WT plus OT. Okay, that the right hand side if you look at the unit on this, it's just hours per period, or just hours. Okay, so this should be the production constraint. Okay, a lot of times it's nice to actually just have my variable on the left hand side alone. So I might write it like this: PT is less than or equal to 8 times 20 WT plus OT divided by 3. So I'm now ready to move on to the next constraint. I also have to think about the constraint on my overtime hours. So number of overtime hours are affected by a couple of my decision variables. The total number of overtime hours per period is going to be affected by, it's going to be limited by really the total number of workers, which is given by WT, and the allowable OT hours per worker per period is going to be 10 hours per worker per period, or I'm going to write month here. So our period is actually a month, so you can use that interchangeably. So then we're actually ready now to write the overtime constraint. OT cannot exceed 10 times WT. Again, you check the units. We have hours on the left hand side. On the right hand side, if you multiply 10 times WT, you're again left with hours per month or hours per period. On the left hand side, again, it's hours per period as well. So we're done with the overtime constraint. Let's move on to the next constraint. We need to create the inventory shortage balance equation. So we know that inventory is going to be affected by the initial inventory / shortage. So I'm actually going to, this constraint here is very, very important. This balance equation is going to dictate the inventory and shortage in my formulation. So the initial, I'm going to use blue here. The initial inventory I'm going to denote as I0, and the initial shortage I'm going to denote as S0. Okay. Existing inventory. So let's say I'm in period T. Then the existing inventory at the beginning of the period is going to be denoted as IT minus 1 if I'm in period T. Okay, so this is the inventory that I ended it with at the end of the last period. Forecasted demand, which is given by DT. Production in current period, which is PT. And then shortage in the current period, which is ST. Okay. Some of these I already know from what's given. I know that I0 is 500 and S0 is 0. So initially I have 500 units in inventory. If I have positive inventory, I can't have a positive shortage. So we know it's 0, S naught is 0. Okay. So let me write an equation when I don't have any shortage, what the inventory equation looks like. So without shortage, then my formulation is very simple, right? So the ending inventory for any given period T is going to be my initial inventory, so the inventory I start with the beginning of the period, plus the production units for that period minus DT. Simple, right? So that's that's going to be my ending inventory if I don't have any shortage. Okay. But if I were to introduce shortage, then I need to modify this equation a little bit. And to think about this, if you think about it, inventory and shortage are binary constituents. Okay, they are opposites. Okay, if you have inventory, you can't have shortage. If you have positive shortage, you can't have inventory, and vice versa, right? So, with shortage, then, so I'll write this in pink. It's actually just a very simple modification. Okay, all we have then is IT, and I'm going to move the initial inventory value to the other side, and then I'm going to add my shortage, ST minus 1, and I'm going to add in the rest of my variables. So you see they're binary conditions, as in you have IT on the left hand side and you have ST on the right hand side. You have IT minus 1 on the left hand side, you have ST minus 1 on the right hand side. If one of them is positive, then the other one has to be 0. Now I need to set the balance equations for the workers. The number of workers that are contributing to the production process is affected by the initial number of workers, which is given by W0, the existing number of workers, so the number of workers that I'm going to start with in that period, WT minus 1, the number of hires, HT, number of firings or layoffs, call it FT. Okay, so then I'm actually ready to create my worker balance equation. My initial number of workers is 50, so this is the end of December and the beginning of January in this scenario. Then my number of workers for any given period T is given by the number of workers at the end of last period plus the number of hires minus the number of fires. To summarize all of the constraints that we just put together, putting all the constraints together, we have the production constraint, PT less than or equal to 8 times 20 times WT plus OT divided by 3. Again, if you're not sure, check the units to make sure they correspond. If the units are wrong, that means you made a mistake. The second constraint, overtime constraint, OT has to be less than or equal to 10 times WT. The inventory shortage balance equation, the initial values for the inventory and shortage, and the inventory shortage balance equation given here. Again, you can think of inventory and shortage as binary conditions. If one exists, the other one has to be 0. Worker balance equation, initial number of workers, the number of workers in period T is the number of workers at the end of last period plus the number of hires minus the number of layoffs, so there's a typo here. This should be FT because I used F for firing, not LT. We're actually missing one constraint, and that's just the non-negative constraint, which says that all variables have to be non-negative. Okay, so we can't have negative number of workers, we can't have negative overtime hours, etc. So we have to enforce that all variables are non-negative. We're now finally ready to put it all together. So putting everything that we formulated into one final formulation, one complete formulation, is start with the objective function. We're minimizing. Again, I'm going to just add this just for clarity. This summation is for the entire equation here. So we're doing this from January to June. So from small t equals to 1 to big T equals to 6. This is my objective function such that all of my constraints are fulfilled. So I have the inventory balance equation here. I have the worker balance equation, the initial number of workers, initial number of inventory, initial number of shortage, the overtime balance equation, the production constraint, and the non-negative constraint. Okay, so we are actually done with this formulation. So what this formulation is telling any solver, like an Excel solver or MATLAB or whatever you use, I want to minimize this expression, or this summation, often referred to as Z. So minimize Z while changing these variables. So remember, this is summation from T equals 1 to big T equals to 6. So there's actually 6 PTs and 6 ITs. So there's actually a 1, 2, 3, 4, 5, 6, 7. There's going to be 42 variables in this problem. So I'm telling my solver, change those 42 variables such that you minimize Z, this summation, while satisfying all of these constraints. Okay, so again, these constraints hold for each period. So again, we have times 6 in terms of the number of constraints we're going to add. So it's actually very easy to do on Excel. This looks a lot scarier than it actually is. If you're interested, you can look at another video on how to set this up on Excel to actually solve. Once we have this, we can look at the results and do analysis. Okay, so that's it. If you're interested in setting this up on Excel, check out my other videos. Thank you.